once we have a series representation of a function, oftentimes we'll want to do some sort of manipulations with those series. And so that'll be the topic of this video, some of the manipulations we do and how they're accomplished. So let's recall we have a series representation for e to the x, which was 1 plus x plus 1/2 x squared plus 1/4, or excuse me, it was 1/6 x to the third plus, and remember the denominators here were factorials, so that would be 1 over 4 factorial x to the fourth, and so on. Okay. So in this case, let's suppose we needed to find a series for e to the 2x. Well, in this case, what we do is we simply go into the series for e to the x, and we substitute a 2x everywhere that we see an x in the original. So our series for e to the 2x would look like 1 plus 2x, and let me keep that in parentheses to indicate that it's what we're substituting, and then plus 1 over, and let me write 2 factorial, and then 2x squared, and then 1 plus 1 over 3 factorial, and 2x to the third, or 2x quantity to the third, plus so on. And what we want to do is we want to pull the x's to the power out of each of those terms. And we could actually take the powers of 2 and reduce some fractions. But in fact, we don't really want to do that. All we want to do is this first term with the 2x, let's just rewrite it as 2x as it is. For the next term now, where we have this 2x squared, quantity squared right here, that of course is 2 squared x squared. This would be 2 to the third x to the third, and so on. So what we want to do is take those powers of 2 and combine them with the fraction that contains the factorial, and then get the x separated away from it. So our next term here would be 2 squared over 2 factorial x squared, and then plus 2 to the third over 3 factorial x to the third. And then you can see the pattern by this point. You can see that the next term would be 2 to the fourth over 4 factorial x to the fourth, and so on. And so that would be our series for e to the 2x. Now we could also do that using just the summation notation. So let's remember that for e to the x, the summation notation was the sum from 0 to infinity of 1 over n factorial times x to the n. So if we wanted the series for e to the 2x, we simply substitute a 2x for the x in the other series. And so we get 1 over n factorial, and then 2x to the nth power. And then we can take that and break it apart just like we did before. So this 2x to the nth is 2 to the n, x to the n. And so what we get in the end is e to the 2x equals the sum from n equals 0 to infinity. We move the 2 to the n to the top of the fraction, 2 to the n over n factorial, and x to the n. So that would be our series representation for e to the 2x, which we can obtain simply from the summation for e to the x. All right, let's try another one of those. For this one, let me have you try this one. So let's remember that cosine of x is the sum from n equals 0 to infinity of -1 to the n over 2n quantity factorial x to the 2n. And using that, let's come up with a series for cosine of negative 3x. So pause the video at this point, see what you can come up with. Try to get that the x term or the x part factored out like we've been doing. And then once we're all done, go ahead and hit play again. And I will do it, and you can see if you come up with the right thing. So now's the time to pause. Okay, here we are back. What we want to do is substitute a negative 3x everywhere we see an x in the summation for cosine x. So we have sum from n equals 0 to infinity. We have negative 1 in the numerator to the nth power. On the bottom, we have still 2n factorial. The thing that changes is now we have negative 3 x to the 2n power. And so all we want to do is take this part out here and separate that, separate the negative 3 to a power and the x to a power. So this turns into negative 3 to the 2n and x to the 2n. Okay, and the negative 3 to the 2n, 2n is always that's an even power all the time. So this would be the same as positive 3 to the 2n. So what we want to do then is when we put that in the numerator, we want to change it to positive 3 to the 2n. So we have n equals 0 to infinity. This would be our representation of cosine of negative 3x. And so in the numerator, we have 3 to the 2n. Yikes, let me fix that exponent so it looks a little better. So again, that's positive 3. Oh, things aren't getting any better there. Well, that's a 3. 3 to the 2n. And then we have negative 1 to the n. And that's over 2n factorial. And then we have our x to the 2n out here. So that's our representation of cosine to the minus 3x. Now what we've been doing here is we've been coming up with new power series by substituting into ones we already know. Now we can do other things with power series as well. And to illustrate that, let me go back to the power series for e to the x, which again was 1 plus x plus 1/2 x squared plus 1 over 3 factorial x to the third plus 1 over 4 factorial x to the fourth, and so on. Now, for the purposes of what I'm going to do, let me rewrite that. That'll be 1 plus x plus, and then this is really 1 over 2 is 1 over a 2 factorial. So let me write that as 1 over 2 times 1 x squared, and then plus 1 over, and let me do the same here, 3 times 2 times 1 x to the third, plus 1 over 4 times 3 times 2 times 1 x to the fourth, and on and on and on. Okay, so let's do this. What we want to do is we're going to take the derivative of e to the x. So let me indicate that with a prime. And what we can do when we take a derivative of something represented by a power series is we simply take the derivative of each term of the power series. Now, this can't be applied with totally reckless abandon, but in this case, you'll see that it in fact works. So the derivative of 1, of course, is 0. The derivative of x is 1. When we get to this next term, we take the power and multiply it out in front here. So we have 2 times 1 over 2 times 1. So that just comes out, the 2's cancel, and we just get 1. And the power of x goes down to the first power. So we get x to the first, or just x. When we go to the next term, and we bring our power out here, the 3 will cancel with this 3. The power of x goes down by 1. So we'll have 1 over 2 times 1 x to the second. And then when we go to the next term, when we multiply by 4, it'll cancel the 4. So we have 1 over 3 times 2 times 1. And that'll be x to the third. So let's clean this up a little bit. And we get 1 plus x plus 1/2 x squared plus 1 over 3 factorial x to the third plus 1 over, and the next one would be, oops, I got my exponent wrong. This is a 3 right here. The next one, of course, would be 1 over 4 factorial x to the fourth, and so on. And you can see that what this is the derivative of e to the x. But you can also see that this series is the same as the series that we started with up here. So what we see is what we actually already know, and that is that e to the x derivative is just e to the x. Okay, and let's do one more of those. Let's take a look. We know that the derivative of sine is cosine. Let's see if it works like that. So the series for sine, remember, was x minus 1 over 3 factorial. So that's 3 times 2 times 1 times x to the third plus 1 over 5 factorial. So 5 times 4 times 3 times 2 times 1 times x to the fifth, and then a minus and dot, dot, dot. So you can see that when we do the derivative of sine, the derivative of x, of course, is 1. When we do our next term, this 3 is going to come out front and cancel with that 3, and the power will go down to 2. So we have 1 minus 1 over 2 times 1, x squared. For the next term, the 5, when you take the derivative, will cancel with the 5 in the denominator, leaving us with 1 over 4 times 3 times 2 times 1, x to the fourth, and then the next term will be a minus. And you can see that this is the first 3 terms of cosine of x, of the series for that. So this is, in fact, cosine x. So that pretty much concludes this video on how we manipulate power series. So we've seen generally what power series are, and then the common power series for e to the x, sine x, and cosine x. And then in this video, we manipulated some series. In the last video that I'm going to do in this series, we'll see how we take a look, how we find out where a series converges.